Friends, today we will discuss about GLM 5.1. This isn't just a small update, it's a massive leap for autonomous AI.
Hello friends, welcome to my YouTube channel. My name is Prathmesh. Without wasting our time, let's begin. And if you like, please like, share, and subscribe.
If you build software today, your workflow likely relies on the prompt and response interfaces of major frontier models like ChatGPT or Claude. You give an instruction, the model generates an output, and the process stops completely. Despite their massive parameter counts and advanced reasoning capabilities, these systems function as static oracles. They answer questions, but they do not independently execute actions. This creates a strict human-in-the-loop bottleneck. A developer has to manually highlight, copy the generated code, paste it into an external environment, compile the program, and observe the results. When a runtime error inevitably occurs, that friction multiplies. The developer must capture the error log from their local terminal, copy it, and paste it back into the cloud-based chat window to ask for a fix. This creates a linear dependency. Every iteration requires manual data transfer between the execution environment and the AI, preventing true autonomous software generation. The limiting factor in automated coding is no longer the intelligence of the model itself. The barrier is the architectural constraint of waiting for a human to trigger the next API call. A recent anomaly in the open-source community challenges this entire workflow. It is an AI system called GLM 5.1. Source data indicates this system generated a working replica of the Linux operating system from a single prompt. This extends beyond a basic shell, including 50 fully functional, natively compiled applications. The entire structure was drafted, compiled, and debugged with zero human intervention, and critically, without an internet connection. How does an open-source framework running locally on consumer hardware exceed the performance scores set by massive, cloud-hosted proprietary models? We are going to reverse engineer the architecture behind this Linux replica. Doing so reveals that a local, self-correcting agent loop outperforms pure parameter scale when executing complex, long-horizon tasks. To remove the developer from the equation, you have to embed the large language model directly into a continuous execution loop. This requires 4 integrated components: base model, local sandbox, log parser, and prompt refiner. The base model generates a script with direct write and execute permissions within the local sandbox, running its code immediately. When an error crashes the build, the log parser automatically intercepts the raw stack trace. The prompt refiner formats this data, explicitly telling the base model which line failed and why, feeding it back into context. This creates a closed circuit. The system iterates at the speed of computation, completely bypassing the latency of human reading comprehension and manual data entry. Granting the model direct access to a local execution environment shifts its role from a text generator to an active software engineer. By maintaining programmatic access to a compiler, the model solves complex bugs not through perfect initial logic, but through the sheer speed of continuous trial and error. This local execution loop explains how a comparatively small open-source model achieves higher completion rates than GPT-4 or Claude Opus on massive coding benchmarks. This chart shows the relationship between a task's time horizon, meaning its length and complexity, and the model's overall success rate. For cloud-based API models, the success rate degrades sharply as the task complexity extends. This drop occurs because cloud architecture introduces friction. Network latency slows down every response. API rate limits throttle continuous execution. And as a long chat extends, the model's context window saturates, leading to hallucinations. When we plot the local GLM loop on the same graph, the success rate stays relatively flat, maintaining high accuracy much further along the horizontal axis. Running local inference completely eliminates external bottlenecks. There is zero network latency and absolutely no rate limiting, which allows the agent to execute hundreds of micro-iterations per minute. Furthermore, local state management allows the system to store code updates directly to the file system, rather than relying strictly on conversational memory. This prevents the model from forgetting early architectural decisions during a long build process. For complex software engineering, zero latency execution speed and immediate error feedback prove more effective than raw parameter count. We can now apply these mechanics directly to the case study to understand how GLM 5.1 handled the massive scale of an operating system. A single prompt cannot generate an entire OS in one pass. The system uses sub-agent planning to decompose the objective into manageable tasks, shifting focus to isolate specific targets like compiling a text editor within the OS framework. During execution, the system hits a dependency error. The text editor requires a specific library that the kernel has not yet built. The feedback loop intercepts this failure, traverses the directory tree, and updates the kernel branch to resolve the dependency. Once compiled, the agent returns down the tree to successfully finish the application branch. This continuous computing process runs locally, iterating through hundreds of nested dependencies for hours without intervention. Achieving this level of long horizon generation requires a system capable of maintaining state across complex directory structures over extended periods of time. Moving beyond system architecture, this localized approach addresses a severe risk in enterprise deployment: data leakage. Uploading classified proprietary codebases to third-party servers operated by companies like OpenAI or Anthropic creates a massive security liability. High-security environments require systems to be air-gapped. This means the hardware operates completely offline, physically isolated from any external network. Because models like GLM 5.1 run entirely on local consumer or enterprise hardware, the entire execution and debugging loop occurs strictly behind the company's own firewall. The primary enterprise value of this technology extends past open-source code generation. It is the ability to deploy continuous, autonomous AI agents on highly sensitive intellectual property without violating security compliance. We are transitioning from a workflow of prompting static cloud oracles to deploying continuous, localized agents. AI benchmarks can no longer solely measure the raw intelligence of a base model. They must now account for the speed, autonomy, and integration of the execution environment housing it. The autonomous generation of an operating system proves that AI can now function as a persistent, locally hosted engineering unit. For the past 2 years, software engineering workflows have relied heavily on massive, proprietary models hosted on remote servers. But a new open-source system called GLM 5.1 has fractured that consensus, clearing the strict coding benchmarks previously held by Claude Opus and ChatGPT. The determining factor in its performance relies entirely on its deployment environment. GLM 5.1 operates strictly on local hardware without requiring an active internet connection. To test the limits of this offline architecture, researchers deployed an extreme edge case, commanding the model to generate a fully functional replica of the Linux operating system. The output requirement included the core OS architecture alongside an integrated suite of 50 working applications. The strict constraint applied to this test was the input. The entire generation process was initiated by a single user prompt. A standard next token prediction model attempting a task of this scale would quickly collapse into a hallucination cascade, losing track of its own logic early in the build process. GLM 5.1 processes the instruction through an autonomous agentic workflow. In this mode, the model functions as a series of active states, where the output of one step informs the conditions of the next, rather than processing the entire OS request in a single pass. Understanding this system requires shifting our focus away from total parameter count and examining the exact architecture that makes continuous autonomous execution possible. Enterprise adoption of local models is driven primarily by the need for air-gapped data sovereignty. When developers rely on API-dependent AI tools, they accept the inherent risk of transmitting proprietary codebase logic to external servers for processing. GLM 5.1 eliminates this exposure by establishing a zero-trust perimeter. Every line of code is generated and executed entirely on the user's local hardware. Securing the data locally requires detaching from the massive compute clusters available in the cloud. A standard workstation cannot brute force a massive context window, nor can its active memory simultaneously hold the logic of an entire operating system. This creates a severe hardware bottleneck for any long-horizon coding task. Overcoming limited RAM requires an execution methodology that prioritizes extreme processing efficiency over raw computational force. To produce massive outputs on constrained hardware, the system must mathematically break the project down rather than attempting to solve the entire structure at once. How does a local machine physically begin generating a massive operating system from one sentence? Linear generation, writing code sequentially from line 1 to line 100,000, is guaranteed to fail as the script quickly overflows the context window limits. The solution built into the model is hierarchical task decomposition. The first step in this process involves parsing the initial user prompt and translating it into a high-level architectural blueprint. The model treats each of these high-level nodes as a strictly isolated project requirement. It then applies a secondary decomposition layer, breaking the core components down further into specific functional applications. These subtasks are pushed into a sequential pipeline, queuing them up to be handled strictly one at a time. By focusing compute power solely on the active subtask in the queue, the model minimizes the active context load placed on the local machine's RAM. As one subtask reaches completion, its output feeds directly into the initialization context for the next application in the sequence. The system utilizes underlying orchestration logic to guarantee that these disparate applications maintain the right dependencies to integrate smoothly later. This entire decomposition and queuing process happens autonomously. The user never needs to prompt the model for each individual application. Generating subtasks in strict isolation does introduce a risk that specific software dependencies will fail to align when tested. Standard conversational AI interfaces rely on single-shot outputs, failing completely when dependencies break. Task decomposition allows the system to manage complex project requirements within local hardware constraints by treating the build as a series of coordinated, small-scale events. Even with perfect task decomposition, any continuous code generation spanning a long horizon will inevitably encounter mathematical and logical errors. When traditional AI models fail during execution, they halt the process. They require human intervention to retrieve the error log, paste it back into the interface, and request a fix. GLM 5.1 solves this through its autonomous self-reflection loop. When a generated application fails to compile or integrate, the system registers the exact failure state. It isolates the fault, comprehends the syntactical break in the code, and formulates a specific patch to resolve it. This generate, evaluate, and fix cycle repeats until the compilation succeeds, requiring zero human input. The ability to ingest, understand, and patch its own errors autonomously provides the exact mechanism required to sustain continuous, multi-hour coding without pausing. Coupling hierarchical task decomposition with a persistent self-reflection loop creates a distinctly new operational state. This capability is known as an extended execution horizon. The model manages states over long durations, ensuring that a patch applied in hour 2 does not break the foundational architecture written in hour 1. For the user, the practical workflow is highly detached. You deploy a single prompt and step away while the machine orchestrates hours of localized labor. By the end of the run, the model has individually resolved and compiled all 50 applications, integrating them back into the master Linux OS framework. This continuous build process replaces the repetitive manual prompting loops required by current web-based AI tools. And this massive compute effort occurs silently on edge hardware, completely detached from cloud server latency and bandwidth limits. An extended execution horizon redefines the developer's role from a line-by-line coder to a high-level systems architect directing an automated workforce. Generating a 50-application operating system from one prompt relies entirely on rigorous task decomposition and precise self-correcting loops. Superior coding performance is no longer strictly tied to the massive parameter sizes of cloud models. For enterprise and secure environments, this offers a direct method to attain top-tier AI capability without compromising proprietary data over an API. As these open-source local agents become more mathematically sophisticated, the infrastructure required to build massive software projects will continue to shrink. Systems like GLM 5.1 prove that the future of high-stakes development is local, strictly secure, and entirely autonomous.